Okay. Yeah.
Okay.
Thanks for organizing this nice workshop and for inviting me to participate in this discussion. I have some sort of disorganized thoughts, but at least it should be pretty quick.
Sorry, Douglas, if I just interrupt you. So the plan for all participants is we're going to have 3 short presentations, and we ask you to not ask questions during this time, but then we're going to open it up and please everybody get involved. Yeah, sorry.
Okay, is it okay if the person presenting asks questions during
that's the whole point, yes.
Okay. So anyhow, so let me just start with this. The most precise version of holography, the gold standard, is some kind of exact equivalence between a bulk string theory and a boundary theory that's actual quantum field theory. And part of what maybe we can discuss in the discussion today is this vaguer, less precise notion that I'm not really sure to what extent it makes sense, but seems to make some kind of sense, of correspondence between a low energy effective theory of gravity and some kind of formal ensemble of quantum theories. So I think that often when we think about holography and bulk computations, we don't use the full string theory, we use some kind of low energy effective theory. And we could ask, to what extent does that description have some kind of a dual? And I think it's to the extent that it has a dual description, it's dual to some kind of formal ensemble of theories. And one point about this is that the correspondence seems to go beyond just random matrix theory or ETH. It's a little bit more detailed, that you can compute small corrections to random matrix theory on ETH from the bulk perspective. Okay, and then one final category is some special theories where it looks like it's part of this imprecise holography, but it kind of turns out by accident or for some reason that it's precise. So an example of that is pure dilaton gravity, which is kind of in the spirit of 2. But it turns out that that theory is completely well defined, and it's dual to something that is also completely well defined. So in some cases, this imprecise holography can end up being, in some very special cases, it can end up being precisely defined. Okay, so I have some questions that I'll come back to in 1 second. But one comment I want to make about this imprecise version is that it's surprisingly detailed. And I want to report one kind of small new fact about this. So first, a nice topic to discuss here is the 2-point function of operators, the 2-point correlation function at long times. And this was discussed by these authors, Bill Mertens Rochelda, and especially by Saad. And they showed how to compute this in JT gravity with matter fields. And they got this curve, which is, as a function of time, which is what you would expect based on a formal ensemble of quantum theories. And it's quite a detailed curve, so that's one point. But what I want to mention briefly is that, just as an example of how detailed this correspondence is, you can dress this up a little bit by studying a theory that has time reversal symmetry and also -1 to the F symmetry. And in that case, if you think about this problem from the boundary theory, you would conclude that this 2-point function as a function of time can have different kinds of behaviors depending on the algebra of the time reversal and -1 to the F operators. And in some cases, it might be that it goes to 0 without having this ramp and plateau. On average, that is, it goes to 0. In some cases, it looks like this, like what we had before. And in some cases, it has a ramp, but no plateau. The late time value is 0. And the bulk theory can reproduce all of these behaviors. And one thing that I want to point out, I think is really interesting, is that in this case here, the reason why the function goes to 0 at late time is because of a cancellation between this sort of space-time d-branes that give the plateau, and an ordinary cross-cap diagram. So cross-cap geometry and these space-time d-branes can somehow conspire together to give this correct behavior. Okay, so let me just list here some questions about this. So coming back up to these three items, 1, 2, and 3, does 2 really exist? How precisely does this imprecise holography exist? Why does it exist? Is it related to 1? So in particular, are the explanations of the late time behavior of 2-point functions, of spectral statistics, of the page curve, to what extent are these things, the explanations of these things in theories of type 2, are those related, do they work the same way in theories of type 1? And then finally, this might be kind of not super important for the, well, not super important for anything, but just as a curiosity, you could wonder if there are more examples of type 3 where it ends up sort of accidentally being precise correspondence. Okay, that's all I wanted to say, so thank you.
All right, thanks, Douglas. Like I said, we won't be having questions now, so keep all your interesting questions for after the 2 other presentations. So who is going next? Is it Raphael or Steve?
I don't care, Steve, whatever you want to do.
Why don't you go ahead then? You can share your, I've hopefully made your iPad a co-host.
Yeah, just a sec. Okay. All right, so I had assumed that Douglas would at least mention this problem of factorization, which he's, contributed important insights to. But since he didn't, I will just briefly mention it myself. So one issue that has led people to this idea of ensembles is the fact that in the gravitational path integral, there aren't, if you have 2 boundaries, there aren't just geometries that fill them in separately, but there are also geometries that that connect them, which destroys the factorization of the partition function. But on the other hand, that's something that you can understand straightforwardly in an ensemble. So I wanted to mention that because I think that is the context that is a little bit better understood, that points towards ensembles. But I wanted to add that I think these beautiful calculations that came out last year by Pennington and simultaneously by Almeri, Engelhardt, Maxfield, and Merolf, where an island gives you the page curve, that those actually also have aspects in them that point towards the necessity of an ensemble to really make sense of them. And I want to discuss this briefly. So this is something that I discussed in a paper with Maria Tomasevic last year, and then in more detail with Liz Wildenhain this year. And these pictures here are out of that latter paper. So just to briefly review the story of the islands and the page curve, suppose that we collect radiation in some reservoir, which could be outside of the space-time, or we could put it here at Scri+. Then in the semi-classical calculation, a la Hawking, this radiation is entangled with interior Hawking partners here. And after the page time, there is so much entanglement that if you apply, so now let's apply the Ryuta-Yanagi formula, right, which tells you that the true entropy of this radiation is really the generalized entropy of the entanglement wedge of the radiation. And the entanglement wedge of the radiation includes an island if that leads to a lower generalized entropy. So after the page time, that is indeed the case, because you purify all of this Hawking radiation with the interior partners and you pay a price in area that's less than this entropy. So this does indeed bring down the entropy. You want to include this island. So this is sort of the step, though. So it's kind of a schizophrenic analysis, right? It's very important that you start by doing the calculation Hawking's way. If you do that, the entropy keeps growing because the state of the radiation computed a la Hawking is thermal, it's mixed. And it's very important that it keeps growing, because if it didn't, there would be no motivation to include this island to reduce the entropy, right? So it's the fact that you do it Hawking's way that forces you to include the island and then get the answer that somehow actually the radiation entropy is much smaller, it's going down, it ends up being 0 at the end. So this is an interesting story. Of course, you could just say, maybe this calculation is a black box and we shouldn't pay too much attention to this intermediate step where we pretend that things work Hawking's way and the radiation just keeps on having bigger and bigger entropy. We keep the final answer, which we like a lot, and we forget what we did in the middle. But it's interesting. I mean, you could worry about the fact that it was very important to take this large entropy seriously in this calculation. And it's at least interesting to note that in an ensemble interpretation of this calculation, this tension is completely resolved. There may be other ways to resolve it that I'm unaware of, but this certainly does resolve it. Namely, if we assume that this semi-classical calculation really computes the ensemble average of a large number of unitary theories, which have the property that the ensemble average of the outstate, each of which is pure in each individual theory, but the ensemble average gives you Hawking's outstate, gives you a thermal state. There are, of course, not in general such ensembles available. There are some examples that Douglas mentioned where they are available. If there is such an ensemble, then it is indeed the case that the ensemble average of the outstate has growing entropy. In other words, S of ensemble average keeps going up. But of course, it is true that in every member of the ensemble, the outstate entropy follows the page curve, since at the end, the outstate in every single member is pure. And so, of course, then the average of those entropies also follows a page curve. In other words, the entropy is a self-averaging quantity and the outstate is not. Okay, so here we don't have a contradiction. This curve pertains to the entropy of the average state, and the yellow curve pertains to the average entropy of the state. Just two different things in an ensemble. So what do we make of this? So I guess I will try not to overlap too much with what Douglas said, which I disagree with. Sorry, which I agree with completely. Excuse me, Douglas. It's fine when that ensemble exists. Then this clearly makes some sense in the context of JT. And in that case, I think we can take every step of this calculation seriously, including this intermediate one where we do Hawking's calculation, the horizon is smooth, and we have all this entanglement. But in this ensemble of theories, well, the ensemble average outstate really is mixed. I don't think we want that to describe the real world. If I did an experiment where I form a black hole and I watch the radiation come out, that should be described by a single unitary theory. Even if we don't know yet what it is, we can just measure the couplings once and for all, and then we know which theory it is. And let's suppose we've already done that. And so that's the theory we should be working with if we expect unitarity. And I think we don't know how much we should, how seriously we should take this intermediate calculation in a situation where we deal with a single unitary theory, the one that we think should actually apply to a real experiment. I think what we can say is that the gravitational path integral is expected to compute quantities that would be self-averaging if an ensemble did exist. We don't always have an ensemble like in ADS5 × S5. In other words, the gravitational path integral would be able to determine some self-averaging quantity like the average entropy, but not a non-self-averaging quantity like the outstate. This, I think, isn't inconsistent. I mean, the gravitational path integral is at present an uncontrolled approximation, particularly in these higher dimensional settings. We pick the saddle points that we like, and we throw away the ones that we don't like, and then we get answers that we want. But it's not known how to use the path integral to compute the exact outstate, for example. And the point that I'd like to make is just that even if we succeeded in finding a bulk theory that does produce the correct outstate, this would have to be sufficiently different from Hawking's calculation that we can't then expect that the horizon in that theory should be smooth. So, there would be significant extra terms that would have to restore unitarity, for which we currently do not have a bulk interpretation. So I think I'll leave it at that and just hand it over to Steve.
Thanks a lot, Raphael. Can you maybe unshare your screen?
Oh yeah. So,
and then Steve, if you can.
I'm trying. Oh, wait a sec. Here we go.
Yeah, great. Awesome. Thanks.
Okay.
Let's see if it works.
Can everyone see that okay?
Yeah, it looks perfect. Go
Great.
ahead. All yours.
So thanks for the opportunity to make some comments in this very nice workshop or conference. I think I'll say a few things that more or less follow up what Raphael just said, and maybe amplifies on some aspects of that. So what does averaging bias, and more importantly, perhaps, how? So a group of islanders, you know who you are, there's a bunch of you are here, have recently found clever rules which reproduce the page curve. And so that, of course, has been viewed as a great success. But there's a key question here, which is the relation of this derivation or reproduction of the page curve to the underlying unitary amplitudes for black hole evolution. And I'm going to discuss that just to emphasize from the bulk viewpoint. And really, there are two sub-questions of this key question, which I'll tackle in turn. So a first question, which I'm puzzled about, and maybe we can discuss, is what is a sensible set of quantum rules to be using? And so here, let me mention a possible answer. And this is something that Joaquin Turiachi and I looked into in more detail in this paper. So one possible answer is that when you look at the underlying amplitudes, you have topology change, like we thought about, even going back to the 80s, where, for example, the universe can split off a baby universe, and so change to something that is disconnected. So you have underlying amplitudes that look like that, and then based on that, you have standard quantum rules then for computing density matrices, entropies, and so on. Basically, you can compose these amplitudes, you can take traces to form density matrices, you can compute entropies, et cetera, et cetera. So if that's the underlying set of rules, you do, for example, obtain broad connections from these traces. But it doesn't look like you really end up with what amounts to a sum over all replica topologies and geometries, like has been discussed in some of the recent work. In fact, I think there's a question there. If you do sum over all replica topologies and geometries, what is the underlying consistent set of quantum rules that corresponds to? Or are you even somehow modifying what you mean by quantum mechanics in that context? I think that's a very good question. But I'm going to assume this answer, what is a sensible set of quantum rules? I'm going to assume the answer is we have topology changing amplitudes, and then standard quantum rules for computing, the things we want to compute. And that's where wormholes and topology come from. If that's the case, then we arrive at something like this story, which we developed back in the 80s, the wormhole calculus and alpha vacuum. So just a quick mini review of that. Goes back to some work by, of course, Coleman and myself and Strominger. So if you sum over all of these topologies, you end up effectively, at least in a good approximation, in a certain approximation, you end up effectively replacing the Lagrangian that governs evolution, say in our universe, by a new Lagrangian where you have these baby universe creation and annihilation operators. And those couple to certain operators that affect the fields in our universe. Now, you can have various states of this baby universe system. And the general baby universe state is going to essentially amount to a superposition of coupling constants as seen by our universe, or an ensemble average. So we can write these so-called alpha eigenstates as the states that diagonalize A plus A dagger for a given baby universe. And so the generic state down here is just some superposition of those alpha eigenstates. And when you make measurements in our universe, the story went, you collapse the wave function to an alpha eigenstate. So effectively you project into an alpha eigenstate. And then, there alpha I plus alpha I dagger for each I is diagonal. And so you effectively have a Lagrangian which has just been shifted by coupling constants that correspond to whatever the alpha eigenvalue is. At that point, once you've done that, once you've made enough measurements to collapse the wave function, so to speak, then you just have ordinary quantum evolution with this Lagrangian. And so that was the essential story. I have this little asterisk that really you could take into account interactions of baby universes. There's a slightly more complicated possible story there. It's not clear that that matters for this discussion, although perhaps it does. But if that's the situation, now let's think about black hole evolution in such an alpha eigenstate. And the question is, how can it be unitary? Because once you're in an alpha eigenstate, you're back to just evolution by good old local quantum field theory, just with some new coupling constants. And so, that suffers the same, problem or challenge that we've been faced with all along. How do you describe unitary black hole evolution in a local quantum field theory? It seems that the only way that you might imagine, modifying the original paradox we found ourselves in originally through this story is if you have some effective operators summarizing the effects of the baby universes that are, non-local on much longer distance scales than, say on distance scales comparable to the event horizon scale. That would be an example. But then if that's true, there's a question of how do these, in fact, manifest the right kind or amount of non-locality to give you unitary evolution of black holes. There's a precise thing that they need to do. They need to transfer enough information out of the black hole to, in the end, give you a unitary description. You can quantify the amount of information transfer. It's basically 1 qubit per light crossing time. And in fact, one quantification of that is looking at effective interactions and parameterizing them that achieve that needed amount of information transfer. Okay, so it's not really clear in this description what is going on that in the end, in an alpha eigenvalue or alpha eigenvacuum makes the evolution unitary. What is responsible for underlying unitary amplitudes? So the moral I tentatively draw from that, although I'm mainly asking questions here, is that it looks like you can average if you want. You can consider an arbitrary superposition of the alpha eigenstates. But there's a question, what does that really buy you? Or, if it is somehow, if the story is telling us that you have unitary evolution, how are we getting at that answer at the level of the underlying amplitudes? So that's about all I have to say on this, and I'll be happy to open up for discussion. I'd be interested to hear what people think about answers to those questions. Thanks.
All right, thanks a lot, Steve, and let's thank our three panelists for the very nice presentations and for opening questions up. So now the floor is everyone's, so it's really everybody's job to join in and discuss. And let's start with Daniel Jeffers that posted a question in the chat, but maybe Daniel, if that's okay with you, you can just ask your question out loud. You should be able to unmute yourself. Or if you can't, please raise your hand and then I'll do it for you.
Looks like you can't unmute.
Yeah, and I can't see people that are raising hands. Let me take care of that quickly. I do think people need to raise hands. Oh, there we go. Yeah, you should be able to unmute yourself now then.
Okay, yeah.
All right.
There we go. Yeah.
Go
It's a strict protocol here. Okay, well, right, yes, I wrote this thing out just so I wouldn't forget it while we listened to everyone's interesting presentations there. Well, I just want to say is I forgot exactly now what Raphael had said that made me think to say this, but I mean, when we ask like what's missing in the Hawking calculation, for instance, presumably the thing that's wrong is that, and maybe this also connects a little bit to Dan Harlow's talk, where if sort of naive calculations in JT or whatever would look like there's a remnant. If you just do canonical quantization, and what's the thing that's missing there? Well, the thing that's missing is that it looks like there's an enormous number of states just from semi-classical gravity, right? So after, let's say you have a black hole that is at least half evaporated, and the interior has grown to a size of order the entropy. So the dimensionality of the Hilbert space of the stuff in the gravity theory is going to grow to the same amount, approximately, just by the volume, and it would be bigger than the Bekenstein bound. That's basically when the page curve is supposed to come down. So if you did like semi-classical quantization of the states of gravity plus some matter, or in higher dimensions could be pure gravity, once the spatial slice has grown to the point where the black hole is half evaporated, you would count there to be more entropy than the Bekenstein bound. So you already looks like there's a remnant. We think the entropy of the black hole is bounded by the horizon area, and that must be because there's null states, right? Many of those states are redundant or proportional. There are linear relations between them. So similar to what Henry and Don studied in the context of the Hilbert space of closed universes. But I think for unitarity of the black hole information, that doesn't require disorder. In other words, having non-perturbative corrections to the inner product could happen in a theory where the Hilbert space of closed universes is one-dimensional, right? They're sort of two separate questions. Of course, in the examples that seem easy, one gets this disordered. That is, we get a non-trivial Hilbert space of closed universes, so therefore holography looks disordered. And if it wasn't like that, of course, then you would be able to compute the exact spectrum of microstates. So it surely will be hard in the cases that don't lead to disorder, because it has to have the full information, right? But I guess that's what maybe we might think happens in like type 2B string theory, A is 5 times S5, right? Okay, it was more of a comment than a question, I guess. That was all I really said. I think I'm reading what I wrote.
Thanks, Daniel.
Maybe other people have a response to
Yeah.
that. Maybe more interesting than me saying it.
Would one of our panelists like to respond?
Yeah. Right.
Oh, sorry.
Oh, well, please go ahead, Yasunori. Yes, just a quick comment before you do.
Yeah, about this.
Okay.
Yeah, I think I kind of agree with the picture that even at the semi-classical level, even before talking about this, you can have a large volume, spatial volume inside a black hole at late times. So it seems like if you regard that all the semi-classical configuration on that huge volume to be independent, you're already oversaturating Bekenstein-Hawking entropy. But on the other hand, we know from the various analyses, including even Juan's late time black hole thing, seemingly independent states of the semi-classical theory have e to the minus s, or s over 2, I think, size of the overlap. So in fact, it's not really orthogonal. And that will reduce the number of independent states to be Bekenstein-Hawking. In fact, you can see this from the other side. If you see black hole from outside, or CFT, holography, you have only E to the S Bekenstein-Hawking amount of independent states. But you can have a double exponentially large number of almost orthogonal states, as is known that if the dimension of a Hilbert space is huge, the coefficient is 1 over square root n. And then if you take a typical inner product of any state, and then it has e to the minus s over 2 overlap. So it's almost orthogonal. Orthogonal state, number of orthogonal states is e to the s. So therefore, the way to include this overlap is to do Euclidean path integral and include all these topologies. That's the way to take into account this exponentially small overlap. And Steve's question is like, what's the principle? The principle you could take as a unitarity, as viewed from exterior. That's a little bit closer to Dan's talk. And from low energy point of view, the principle could be locality and Euclidean, unitarity. A Euclidean path integral or nice slice. General covariance locality is obvious, but you could put unitarity is not obvious. Therefore, you have to restore that by including Euclidean gravitational path integral to make e to the s to the e to the s. From the other, a distant part, a unitarity is obvious, like stretched horizon and everything, but interior has to show up in a more subtle way. So you can, from low energy point of view, you can just take these two as a definition. But anyway, I'm saying like Daniel's picture kind of agree. I have one more comment, but I will just stop here. It's getting long. So.
Thank you. I think Juan had a comment, and then we can maybe turn back to our panelists. And
yeah, so I think the previous comments seem to say, if I understood them correctly, that in the interior of the black hole, the states could not be all non-orthogonal, right? On the other hand, I think we want them to be somewhat non-orthogonal in order to be able to entangle them to the radiation, right? Or just we want the page curve picture. Imagine a very late time black hole where we have a very tiny black hole. The states, these various states in the interior should encode information about the various states that went into the black hole, right? So we need to have, I think, some kind of richness. Of,
I was saying e to the s, not the e to the s, but e to the s is still there. It's not the dimension 1, of course. It's just it's Bekenstein-Hawking entropy.
Well, what I was saying was, well, okay, yeah.
Yeah, the rest is radiation, and then this saturates just entanglement. The smaller the Hilbert space.
Maybe one is what you mean, that it's not that we should, of course we shouldn't think of some null states existing entirely in the interior as if it was a factorized piece of the Hilbert space, but rather in the total accounting, which includes both the interior and exterior, although probably when the interior is much larger than the exterior in a sense, it might be mostly in the interior, but that's not a totally precise statement. Is that what you meant? So in other words, that the null states are in the full Hilbert space, which contains both inside and outside. Or did I misunderstand?
Well, my only comment was that the discussion seemed to assume that the interior was part of the black hole Hilbert space. But
okay, yeah, I got it.
Well, I would have thought I would have thought that it's the redundancy of these states as written in the bulk language, which makes it agree or compatible with the fact that the interior operators can be encoded in the radiation. It's because the interior, what you thought were different interior projectors aren't actually distinct, so that they're equivalent to some exterior observable. I mean, it's a little bit like the black hole final state, except not as extreme if you don't go all the way to the end, right?
But I think there's a question associated to this. You know, if you think about quantization, about the semi-classical geometry, right, then we have a situation where we build up entanglement between the interior and the exterior radiation. We can effectively think of the black hole interior as forming a subsystem, right? And you have the entanglement between that subsystem and the exterior. And you've got to have some new effect that significantly modifies that. So, you know, what is it from the bulk point of view? And it's, I think, been hard to identify that at the level of some interaction or what have you. In effect, you have to, if you have null states, you've got to have some explanation of why all of a sudden you don't count the internal states as being part of your internal Hilbert space. You're re-identifying things so they're part of, you know, some other subsystem. So, or you could have interactions that effectively are transferring the entanglement out, but what are those interactions? So I think that's part of the question that we really need to understand the answer to.
I think Douglas.
Let me do one thing, because Juan's thing. Juan, I think I understood what he said, and I agree. I just stated like a large volume inside the black hole to just illustrate overcounting, but the residual non-locality should be there, right? The radiation must be involved. I agree. Yeah.
Yeah. So Douglas.
Yeah, just a comment about Daniel's question in the context of Raphael's talk. You can compute the inner products of these states using the same methods that you use to compute the page curve. And what you find is that that it's zero, but the square is non-zero. And again, that's something that seems to require an interpretation by an ensemble.
That's in JT gravity, or do you mean more generally, Douglas?
I think it's more general because this comes from a semi-classical calculation, like not too different from the page curve. So yeah.
That I don't, can I comment on that? Just, I think your calculation, like the critical part of that ensemble from boundary point of view is needed is inner product being zero and inner product square being e to the minus s, right? So inner product, unless inner product is zero, you don't need that. It's just e to the minus s. I think in higher dimension, what happens is e to the minus s, because you got zero, because you can put the degrees of freedom on the end of the wall plane. That's a kind of Chamberlain factor, but I don't think you can do that in a higher dimension. That's just I don't know. I'm not sure, but that's my guess.
Okay, so we have a question by Steve. Steve, please unmute yourself. And
I'm sorry, can I just say something about this?
Sure, go ahead. Yeah, please say something, and then we'll pass on to Steve. Yes.
Just going back to Danielle's question, I guess I would agree that, you know, we obviously need to examine what's missing in Hawking's calculation or where he went wrong, and you know, that's one of the big questions. But I would just stress that it is the fact that we followed Hawking's calculation here that gave us in that step a smooth horizon, and it's also the fact that we followed Hawking's calculation that made the RT prescription work out for the page curve. And while we can speculate about modifications to that, I think the tangent, and I think AMPS really sharpened this tangent, is that it seems that the required modifications to get a different answer are precisely of the nature where you destroy those properties. And so I think the challenge is not only to say where Hawking went wrong, but to make him be wrong in a way that doesn't destroy those nice properties.
If I could say one quick sentence.
All right, one sentence. You guys had us
Okay, well,
for a long time. Go ahead.
Yeah. Right. I mean, I guess I thought that what seems suggestive to me about this possibility that the state computed by the Hawking calculation is correct formula. It's just not written in a basis. Is that imagining that that's a basis was also an assumption of the AMPS argument. So insofar as the AMPS argument would apply, then the state computed by Hawking would be unmodified and things would work
But that's
nicely.
thermal, right? So the fact that it's thermal and not pure is independent of any basis.
No. I mean, that's only when you trace the interior. I mean, don't trace the interior. Well, maybe we should talk about it later. Yeah.
All right, let's give the floor to Steve. You can unmute yourself. Yes, great. Please go ahead.
Yes, I wanted to just raise the question about whether this non-orthogonality of states that several people have measured, that seems a crucial ingredient in these developments, the detailed nature of the energy spectrum, that would be required to specify, let's say, an alpha state. To compute these things, is geometry enough? Computing wormholes, other kinds of gravitational instantons, or do we need for, let's say, the UV completion that Daniel Harlow mentioned? Do we need strings and brains, et cetera, in a crucial way? This is a question that people in the fuzzball program argue about. And in this context, I just wanted to highlight this recent paper of Lorenz Eberhardt that in a toy model, another toy model, the tensionless string, where they see a hint of this modular invariance that Daniel Harlow mentioned, as creating this equivalence between, a high temperature gas of strings on thermal ADS and the Euclidean black hole. And to what extent do we need to understand these kinds of degrees of freedom to really see what's going on? Or can we build an effective description without them, or do we need, or how much more do we need than geometry? That's the question I wanted to raise. I'll stop there.
Thanks, Steve. Would the panelists like to comment, or anyone else?
Well, effective description of what?
Well, for instance, of factorization. Can you, let's say, can you understand how factorization works, but then some kind of averaging, time averaging, for instance, removes the pieces of the factorization you don't want?
Sorry, do you mean leads to non-factorization?
Yes. So this will be something that Phil Saad will talk about in his talk, but what do you need to understand? Well, let me just phrase it as a general question. If you want to compute let's say you wanted to compute more details of the exterior S matrix, how much detail of the black hole S matrix can you compute without understanding, like the numbers in the S matrix, can you compute without understanding strings, brains, et cetera, in the bulk description? How much can gravitational geometry take you in that direction?
Yeah, I think if I may say something, I think this is possibly related to Douglas's 3 points. I mean, or maybe obviously related to Douglas's 3 points. How do you transition from, say, his 1 to his 2? Or how do you add something to 3? So, I mean, I was trying to perhaps argue a little bit in my talk today that, I'm sure Douglas is probably of a similar opinion, but one can take one's clue there from actually understanding this ensemble averaging in quantum chaotic theories, meaning that, there, obviously you can go from something like 1 to 2, right? You can have a very detailed theory, an individual theory, and you can still associate an ensemble to it simply because it computes certain observables, especially in the long time limits. So there's an effective ensemble description in the long time limit. You're, I guess, asking two questions, right? You're asking, firstly, how do you do this explicitly in gravity, and how do you see what, is it really the, say, gravitational path integral that describes the ensemble limit? But it could also be asked in a different way, which relates to what Steve was saying. Can you add something to the cases which are understood to be consistently dual to an ensemble like JT, and get signatures of the individual theory? So, for example, the random fluctuations at late times, right?
Yes, that's the kind of question I'm curious, especially in the context of some ADS5 process 5 kind of description or super Yang-Mills.
And I would then say that from what we know already, probably you do have to add such degrees of freedom as you suggest.
Well, okay, I think it may hinge on this question of how you realize the bulk microstates, and so that's the question.
To jump in here, so can we agree that we can at least focus on one member of the ensemble, what I was calling an alpha eigenstate, and then try to answer the question there, for example, what gives us unitary evolution of a black hole? I mean, if we can focus on that case, then the ensemble is put aside. And this, I think Raphael was saying something along these lines as well. The ensemble is put aside, and we need some effects within that context, which are responsible for the unitarization. Does anyone object to taking that point of view?
Well, I think if you start with an ensemble and then you try to do some measurements to end up putting yourself in the particular alpha state, then you'll still end up with the wormholes. They'll just implement some version of the black hole final state, and that's how you'll get the information out. And yeah.
Well, okay, so you're not objecting to focusing on the ensemble, but you're proposing what happens once you, sorry, to focusing on a member of the ensemble. You're saying what you think will happen once you do that. Yeah, I think that's something we really should understand. That to me is kind of at the heart of the matter, in a sense.
Douglas, I thought to do the black hole final state proposal was supposed to happen even without you doing a complicated measurement first, whereas figuring out which alpha vacuum you're in, you might have to figure out which string compactification you're in or something.
Yeah, I didn't say that the ensemble theory is the same as the final state, only that if you do enough experiments to determine the alpha state, then you can ask, like, how do we evade the fireball paradox? Like Marov and Maxfield asked this question in their most recent paper, because then how do we evade the amps paradox in that case? And I think the answer is that it implements the black hole final state. All of the measurements that you previously did to determine the alpha state connect by wormholes to the next version, and that implements the final state.
But would you view that as an evidence that in n equals 4, where there's no average, that we just do black hole final state, that's it?
Well, not really.
Yeah, it surprised me, but I'm just curious.
I think that I only know how to try to support this if we start out with a theory with an ensemble and we do many measurements. Yeah, I'm not sure how to get started.
I can just add something to that. I would say that, to me at least, the key question is, how do we get back from this ensemble picture where there clearly is a smooth horizon to the one where we have a single unitary theory, and in particular, what happens to the smooth horizon when we do that? I mean, it's not so. One way to think about it is the way that Douglas just described, but I think it's also worth noting that, as Douglas knows very well, it's not clear that there's a meaningful way to discuss the black hole interior once you have a final state. And I don't think that's a coincidence. So I think that's sort of where the crux is, at least in my mind.
By the way, is it really clear that the answer is something like the final state if you do focus on a member of the ensemble? This comes back to Steve's question also, maybe some other stringy or brainy effects are needed, or, that's the question. What new effects are needed beyond Hawking's?
The setting is we start with a theory that doesn't have the strings and the brains, and it's some kind of dual to some kind of ensemble, perhaps, and maybe in an imprecise sense. And then we set up the complete experiment that would determine the alpha state. And then we say, now we run black hole formation and evaporation one more time and ask what happens there. And so you don't need the strings and the brains to answer that question.
Well, but we do need to say, in that context, once we've collapsed to an alpha eigenstate, in one way of putting it, what is the correct description of the unitary evolution that, gets, it tells us that we have a pure state for the final state of the black hole evaporation.
Right. What I'm trying to argue is that the answer to that question is that it's the Horowitz-Maldacena black hole final state proposal. That's the way that you get the unitary evaporation.
Was that absolutely clear to you, or how do you get to that statement?
The black hole interior can connect by a wormhole to the previous versions of the experiment that you did. And the previous versions of the experiment that you did project on the outcome of that experiment. And that becomes a projection inside the interior of the final black hole that you're measuring.
Douglas, one thing about the original Horowitz-Maldacena proposal, it was seen as important that this was happening at the singularity rather than, say, the horizon. Whereas when it's happening because of wormholes connecting to earlier experiments, it's less clear that that's the case. In fact, sort of seems like it's not the case.
Well, I guess you probably have some freedom about where you put that.
Yeah, it depends on the contour you use, but like it's certainly not definitely at the singularity. That's my only comment.
But I think it's important that if you do put it at the singularity, you have some problems with interactions between the ingoing matter and the inside Hawking partners, which sort of destroy the proposal unless you explicitly undo them.
I think in this case, they will be explicitly undone, because when you do your Schwinger-Keldysh contour, then the backwards part of the contour that connects the other wormhole will undo the same interactions there. Right. But that seems like it's a feature of the fact that we started with an ensemble and then did a load of measurements to determine an alpha state. But this is having like brains or whatever, it's much harder to have that work.
It's sort of difficult to make sense of any phenomena that happen after you cross the horizon in this formalism.
Sure.
Effectively,
I would agree
you want to reflect the state at the horizon.
So Henry has had his hand up for a while. Henry, do you want to ask a question or make a comment?
Yeah, well, yeah, I had a couple of comments, but I get my 45 minutes to make is tomorrow, so maybe some brief ones. So one way to think about this black hole final state and why it's sort of going to be an inevitable description of these wormholes is just to imagine cutting the path integral at the horizon, and then whatever happens inside the path integral involve replicas, wormholes connecting to other copies, previous experiments or whatever. In the end, it just projects onto a wave function. It's a function of the fields on the horizon, which is a projection onto a particular wave function. So that tells you that as long as there's just islands inside the horizon, it's got to have the form of a projector. But perhaps the previous comment, which was to address one of Steve's earlier questions, was that this wormhole point of view makes it clear that there was an implicit assumption in Hawking's calculation, and that assumption was what the initial state of closed universes is. And then when you have exponentially many experiments, enough to determine an alpha state, you can also see it very explicitly in toy models and JT gravity and so forth, that then there's a principled reason to expect the semi-classical approximation to break down. And because the interactions between wormholes become important at leading order, the sum over different topologies simply is asymptotic and doesn't converge anymore. And so you get interesting effects of discreteness of spectrum and so forth has to come from that non-convergent tail of the semi-classical expansion in the sum over topologies. And that is, I think, the place where string brains and so forth are going to play a crucial role in something like ADS ADS5 cross S5, that they complete that sum in such a way that they project you onto an alpha state. This is a cartoon of how you might hope it works.
Would anyone like to comment?
I could make one question here. Like, suppose we work at a time or compute something where like the genus expansion is like, well, it's asymptotic, but it's like almost like it's really convergent, so that the higher terms are really small. Do you think we still need the already the first term gives us some contradiction with factorization, and it looks like it should be a good approximation. You're saying that somehow we're fooling ourselves in thinking that it's an asymptotic series?
Yeah, so this is exactly the confusing point, is if you need the non-perturbative corrections to be somehow large, but possibly very rapidly oscillating as a function of parameters. And so there's got to be some weaker sense in which this is asymptotic series makes sense, where you're not just throwing away things that are exponentially small, but you're throwing away things that are exponentially rapidly oscillating. So it's it is not the usual sense in which we talk about asymptotic series, certainly. But
if you take that viewpoint, can you describe the corrections to Hawking's calculation in a controlled approximation, do you think, in terms of some interactions or something? How do you be more precise about what you've said?
It depends on what corrections you have in mind.
The corrections that are the modifications to Hawking's calculation that are responsible for making the final evolution unitary instead of not.
So if you want to compute the modifications to the wave function,
yeah,
for S matrix elements,
evolution of the wave function would be a good starting point.
Well, I think you can make a controlled approximation where you actually going to a specific alpha state is, I think, is an uncontrolled approximation, but going to an approximate alpha state that has some width that is then you can make a controlled approximation of how that would work in an ensemble type description in terms of the states of baby universes. So one very simple model that I encourage people to play with is one that was suggested by Polchinski and Stranger in 94, 95, which was, that's essentially the approximation you get to, where you have an island at very, very late times that becomes the entire interior of a black hole. And then there's the Hilbert space of closed universes becomes like a bosonic Fock space, where different islands can attach. It's the normal symmetrization that you get in bosonic inner products. And that's a model where you can be incredibly explicit and see how you arrive in a particular eigenstate and so on and so forth. It misses some other nice features. It doesn't quite have the page curve, but as a toy model for these ideas, it's a nice thing to play with.
So we're getting close to the end of the session, but would someone like to make final comments or early comments or any comments?
Well, I could ask one question to Douglas. Did what you said before give a description for the dual of a single instantiation of the ensemble that gives JT gravity? Okay. Can I understand it in that way? Or what is the bulk dual of a single instantiation of the matrix model?
What I said before when
you said if you made enough measurements to nail down the alpha state and then you looked at some future processes, so could you reinterpret that picture as
that would be really trivial. It would be like, I think it would be something like you would insert in the matrix integral some kind of, well, sorry, let's discuss the matrix integral first. It'd be like inserting an observable there that like fixes the Hamiltonian completely. And so then in geometry, we could insert enough things that would fix at least the spectrum of the Hamiltonian by a whole bunch of things involving partition functions. That's some function of the partition function, right? That delta function onto the spectrum. So we would insert that thing in gravity, and it would have a whole bunch of boundaries, and those would connect to whatever we're trying to. Actually, yeah, I think
I guess that was
question is there's a sort of a precise version of this that will be discussed in Phil Sodd's talk. I think so. You can. They're not going all the way to an alpha state, but part of the way, and they sort of explain how it works.
I can comment briefly that, I think this idea of fixing the boundary ensemble is what was discussed in this paper called Eigenbrains by Blomert, Mertens, and Verschuid, and it involves inserting a lot of these D-brain things, and that, as Henry pointed out, genus perturbation theory can break down if you ask very precise questions. You have to sort of do some coarse graining, these approximate alpha state kinds of things, to avoid that breakdown of the genus expansion. And that's a little bit of a way of seeing these issues, very much in the way that Henry's previous comment implied.
Great. So I think we're arriving at the end of the session. So why don't we thank our three panelists again? And also really thank all of you for joining into the discussion. It was really fun. One good part is that I think we've touched both on firewalls and the final stage, which will be the two other discussions of the week. So in some sense, I think it's going to all turn into one long, big discussion mixed all together, which in some sense is kind of the point. So that's really great. So with that, I really want to thank all of you for coming today, and see you all tomorrow at whatever time it is in your time zone. Yeah, and that's it. See you all tomorrow. Maybe I'll